All right, so we are now going to use Gauss's law to solve for the electric field, which has kind of been our purpose here in this chapter. So we know how to find flux, we know how to find Q inside, the charge inside your Gaussian surface, and now we're going to bring all that together. So let me write out what we're looking at. So Gauss's law, right, flux equals charge inside over epsilon 0. And if you have your conditions met with flux, remember the conditions for flux that if we have a symmetric surface that matches the symmetry of the charge itself, matches the symmetry of the electric field. So let me put that here. Put that in. Okay, so if the Gaussian surface matches the symmetry of the charge or of the electric field, because that's what we want. We want the electric field to be perpendicular to the Gaussian surface and constant around the Gaussian surface. Then, so in that case, then we could say that flux equals EA. So E we're not going to know, right? The whole point of this is to find E. But this A, remember, is always the area of the Gaussian surface. Remember in past videos we had lowercase r, uppercase R. This is typically the lowercase r that I'm going to reserve, at least the way I do it, I'm going to reserve the lowercase r to represent my Gaussian surface, the radius for my Gaussian surface, or maybe if we're dealing with the cylinder, the length of it. You know, I guess it does depend on what shape we're looking at. Okay, but that A and E in the flux is always going to refer to the Gaussian surface, and then we have our charge inside. And charge inside, we saw that we could solve for using something like density. So if we're talking about a volume charge density, then it would be Q inside equals rho V. Okay, so that would be the case for a constant or for a uniform charge. Uniform charge density. All right, for non-uniform charge density, then we would do something like this. Q inside equals rho dV. Okay, so this is for non-constant. Constant charge density. Now we don't always deal with volume charge density. Sometimes we're going to be dealing with surface charge density, sometimes linear charge density. So all we would be doing is replacing this rho and this V. So for example, surface charge density, the Q inside will be something like eta times A, right? Charge density times area. Or if it was linear charge density, the Q inside my Gaussian surface, it's going to be lambda times L. Okay, so it kind of depends on what density we're looking at. Typically, we do look at volume charge density more often than not, but these do come up occasionally. Right, the eta for surface charge density and lambda for the linear charge density. Okay, so all this here is to find the charge inside my Gaussian surface. Okay, so you're going to see a pretty consistent pattern when we're doing our problems in a minute. That the first thing we do is draw out the picture, and then we have to decide what our Gaussian surface is, because everything depends on that, right? This A depends on the Gaussian surface. Q inside depends on how you define your Gaussian surface. So that's going to be a pretty important step, that we want to choose the right Gaussian surface, not only so our flux is easy to calculate, but also so that we know what we're finding the charge of. Okay, so let's do our first problem, which is just a simple point charge. Now we know the electric field of a point charge, so I'm mostly doing this to see that Gauss's law works, to give you guys the idea behind this with a simple problem, and then we'll increase the difficulty as we go. So a point charge, let me draw that out. So I might look something. I'm going to set up an axis here. Okay, so I'm going to put my point charge right here. Okay, and let's just say it's a positive Q. Okay, so positive Q. So it's a positive charge. Okay, and the question might say something like, find the electric field at some distance from the charge at, let's say, 10 centimeters from the charge. Okay, it'll give you some value. So I'm just putting that value just as an example. Or we could, maybe we don't put a number. It just says find the electric field at a distance r from the charge. Okay, so sometimes you're going to be finding, sometimes you're going to be dealing with numbers, sometimes you're going to be finding expressions. So let's just find the expression for this problem. Okay, so we have this charge. We want to find the electric field at some distance. So we want to find the electric field, let's say somewhere like right here, right? And that'll be our distance r, which would be the same electric field, same magnitude as anywhere with that radius, right? So if I go, let's say right here, if I have that same radius, the electric field is going to have the same magnitude here as it would here, as it would here, as it would here, right? Anywhere on this perimeter, or on the circumference, I guess I should say. Anywhere on the circumference, the electric field will be the same because, you know, we're going to say equidistant from the charge. Okay, so how do I use Gauss's law to find that? Well, I need to set up a Gaussian surface first. So I'm going to set up my Gaussian surface. Let me see here. Try making it. Okay. All right, there we go. So here's my Gaussian surface. What kind of surface would fit the symmetry here? Well, a sphere, right? So the charge here is going out radially outwards in a spherical manner. So it's going in X, Y, Z, you know, it's going in all directions, but radially outwards. And so I have the electric field from this charge, looking like this. So everywhere on that surface, the electric field is going through it. You can see in my picture here that the electric field is always perpendicular. Okay, and not only is my electric field always perpendicular to my surface, right? It's always 90 degrees to my surface here, but the electric field is constant along the surface, right? Because we have a constant distance from the charge, right? So anywhere on this surface, on this sphere, the electric field is the same magnitude, different direction, obviously, but same magnitude. Okay, so how do we find electric field from Gauss's law? Well, let's start with Gauss's law. Gauss's law says flux equals Q inside over epsilon 0. All right, so how do we get flux? Remember what I said earlier? Well, flux is going to be EA, right? Electric field times area, if your conditions are met. If your electric field is constant along that surface and the electric field is perpendicular to that surface. And that's what we have, right? Electric field is constant, like I explained. Electric field is perpendicular at all points on that surface. So I could just replace flux with EA. Remember, that's the area of my Gaussian surface. And I'll plug into that in a second. And then for this example, it's fairly easy. Q in. What is my Q inside? Well, the charge inside my Gaussian surface here, how much charge is inside, is just this Q. So no fancy calculations needed, just lowercase q. Okay, and we're trying to find E. All right, so let me plug in for area. The area, so we're talking about a sphere. So what's the surface area for a sphere? 4 pi r squared. Okay, and that equals Q over epsilon 0. And let's solve for E. So if I solve for E, so divide the 4 pi r squared over to the other side, I get E equals Q over 4 pi epsilon 0 r squared, which is exactly the equation we got earlier for an electric field from a point charge. Remember we got this, E equals K Q over r squared? Well, this is the same thing. because K could be represented with a 4 pi epsilon 0 in the denominator. Okay, so just a simple example of how you use Gauss's law, and we get the expression that we're used to seeing. This is what we would expect from a charge. Okay, so now we get electric field as a function of r. Right, we could find the electric field at any distance. Okay? All we would be doing is changing the size of our circle, but we could find the electric field at any distance from this point charge. All right, so let's get to a little harder example. That was just more of a warm-up. So let's do this one. A sphere with charge Q that is uniformly distributed throughout the volume. All right, so we've done this in the past. In the previous video, I showed you how to find the charge inside this situation. But now I want to find the electric field. Okay, so let me draw the actual charge. Let me just do it. I know, not black. Do it like this. Okay, and then let me define this with a radius. Okay, this is going to be a capital R because I'm referring to the physical radius of the charge itself, and we know its total charge is Q. Okay, so that charge is dispersed, distributed throughout this volume. Okay, so the question would be something like, here's my question. What is the expression for the electric field due to the sphere everywhere in space? Okay, so when I say everywhere in space, let me just read what I wrote. What is the expression for the electric field due to this charge everywhere in space? So there's different regions of space here. And you can kind of, maybe you don't see it right away, but you have the region inside the sphere. Okay, so I'm gonna call that region 1. Okay, so the electric field inside the sphere, it's gonna behave differently than the electric field outside the sphere, and that's called region 2. Okay, so region 1 is inside the sphere, region 2 is outside the sphere. Okay, all right, so let's first find the electric field in region 1. Okay, so find the electric field in region 1. I want to get an expression for the electric field inside. Okay, well, before I do that, remember we're talking about a volume charge density here, right? Because this charge is has filled up this volume, this sphere. So going back to charge density is Q over volume. And since this is uniformly charged, I'm going to put Q as my total charge divided by my total volume, which is 4/3 pi. Now, capital R or lowercase r? Well, we haven't introduced lowercase r, right? Lowercase r is we are reserving for our Gaussian surface. So I haven't drawn my Gaussian surface yet. So this is just the volume of my physical sphere. Okay, so we're going to use, I put that here because I'm going to refer to that in a second. Let me write that a little bit neater. Okay. All right, so there's my charge density. Now, I want to find the electric field inside region 1, inside this sphere. So let's start with Gauss's law. Right? Flux equals Q inside. Q inside is the charge inside your Gaussian surface over epsilon 0. Okay, so in order to find charge inside, in order to find flux, I need to define a Gaussian surface. Right? This is what I did earlier in the last problem. I had to define a Gaussian surface. So what kind of symmetry should we use here? Well, we have a sphere of charge, so we should probably stick with that symmetry. We should probably stick with a sphere. So I'm going to use a sphere, and I'm going to, whoops, put a sphere in here. Okay, so here is my radius for my Gaussian surface. Okay, so when we're talking about region 1, I'm looking at when r is less than r. Okay, lowercase r is less than uppercase r. That's region 1. Okay, so I picked a sphere for my Gaussian surface. Symmetry matches, right? So now that means my flux is just going to be EA. And my charge inside, let me put my 1 over epsilon 0 here so I don't forget. But what's going to be my charge inside? Well, this is where my charge density comes in, right? When we did this in the last video, that if I want to find the charge inside my Gaussian surface, I need to use that charge density. So charge inside is going to equal charge density times the volume. Which volume though? Which volume would I use to find the charge inside my Gaussian surface? Well, I would use my Gaussian volume. Okay, so I'll put rho Vg, which is equal to, let me just plug in for charge density. Charge density is Q over 4/3 pi r cubed. Okay, so that's my charge density. I got that from down here. Total charge over total volume, right? That's a valid ratio for charge density. And then times Vg, volume of my Gaussian surface. Let's see if I can fit it in here. 4/3 pi lowercase r cubed. Okay, so that simplifies. EA equals, let's see, Q over epsilon 0. 4/3 cancel out, so we get r cubed over r squared. I can write that neater. All right, r cubed. Okay, one last step here. I need to plug in for A. What area am I going to plug in? Okay, well, for area, the area I'm looking at is always the area of your Gaussian surface, in this case, the green sphere. So the area of that sphere is 4 pi, uppercase R, lowercase r, lowercase r. Okay, so E equals 4 pi, or E times 4 pi r squared equals, you know what I have over here. Okay, and then I'm gonna solve. So solve for E and get my electric field. The magnitude of my electric field would be Q R 4 pi epsilon 0 r cubed. Okay, so that's my electric field in region 1. All right, I'll come back to that in a second. So let's look at region 2. Okay, so region 2 is when we're looking at when uppercase R is less than R. Okay, so I'm going to make this circle here larger. Which means I'm changing my radius. Okay, and we start the same way. Flux equals charge inside. Let me do this in a different color. So everything's almost the same. My flux is still EA, so it's still E 4 pi r squared, lowercase r. That side doesn't change. What about the right side? What about the right side? How much charge is inside my Gaussian surface here? How much charge is inside my green circle? Okay, well, in the last video, I talked about this, and the charge that's inside is just all this charge here, which we say it's Q. So charge inside is just equal to Q over epsilon 0. All right, and let's solve for E. It's kind of interesting what we get here. E equals Q over 4 pi epsilon 0 r squared. Now take a look at that equation. So this is for the electric field in region 2. Maybe I could put a little subscript here. Region 2. And up here is the electric field for region 1. Okay. Take a look at region 2, the electric field for region 2. What does that look like to you? K over 4 pi epsilon 0 r squared. When have you seen that before? Well, we just saw it over here. Q over 4 pi epsilon 0 r squared. This is just the electric field for a point charge located at the origin. Well, we get the same thing here. This is the electric field to a point charge due to the origin. So that means once you get outside of the sphere here, once you're no longer inside the sphere and you're outside the sphere, right? You're standing somewhere on this green circle on the Gaussian surface here. This would not look like a ball of charge to you, right? If you had some kind of like glasses that only saw electric fields, what you would see is this charge here, whoops, almost reduced to a point charge. Almost reduced to a point charge at the center. You wouldn't be able to know that it was a ball of charge once you step outside of it. Now, really, we are looking at a ball of charge here. Okay, now to fix it. Okay, so we are looking at a ball of charge there, but once you get outside, the electric field just looks like it's a point charge. Really interesting there. It's kind of, I wouldn't expect that. When the first time I saw this, I didn't expect it. So let me plot this. So let me plot electric field as a function of r. Just to show you how this looks like. Electric field as a function of r. So I'm going to put this little dash line here. This is capital R. So how does the electric field look like as I'm starting from the center, from the origin, from the center of the circle, and going towards the radius, towards the edge of the sphere? Well, it's going to look something like this. It's going to look linear. How do I know it's going to look linear? Well, look at the function that we got. Oh, come on. Okay. Look at the function that we got. We got a function here where it's just proportional to r. All these are constants, right? Q, 4 pi epsilon 0, capital R. These are all constants. Lowercase r is that variable. So constant times r. So this is a linear relationship. Electric field increases linearly with respect to radius. So that's why I drew a straight line. And once you get outside of that, like now we're in region 2. Once you get outside of this ball of charge, here's our electric field. And it starts to decrease to 1 over r squared. So I would draw it once you're on the outside. Looks like this. Okay, well, it doesn't go to 0. Something like that. Okay, and this would just be the electric field for a point charge, right? If you extrapolate it back, it should just look like a point charge, where it starts up very, very high and goes down to 0 as 1 over r squared. Okay. So that's our electric field from a ball of charge. Using Gauss's law, we could find the electric field in both regions, region 1 and region 2. All right, let's do one more here. And then in the next video, I'll really up the difficulty by having something non-uniform. But now let's look at this one. So we have a hollow cylinder of charge with uniform charge distribution. And it's the same thing, same prompts. I want to find, put it here. So find the electric field everywhere. Now, when I say everywhere, I mean everywhere. You should have a function for the electric field at any point in space. So let's draw this out. Let me draw out this a hollow cylinder of charge with a uniform distribution. I'll try to draw it 3-dimensionally here. Yeah, let me try drawing it 3-dimensionally. We shall see. And then I'll draw it 2-dimensionally. Okay, so here's my three-dimensional drawing. So I'm just going to say super long. Probably should have said that in the description. So a long, long hollow cylinder. So we're gonna take it to be infinitely long. Otherwise, we lose that symmetry. So I'm gonna say it's infinite long. And in here's a cylinder. This space in the middle is empty. The charge is residing within here. Okay, that's where my charge is. If you want to see it from a different perspective, you know, if we're looking at it head on, I'm not even drawing my Gaussian surface yet, by the way. This is just a cylinder. Okay, so this is how you look at it. If you're looking at the cross-sectional area, right, looking head on onto that wire, the charge, I could put the charge like this. It's all up there. Let me see. Okay, so that's where the charge exists here. Okay, so ignore those darker lines because I could just do this. All right, now it just looks messy. All right, so I think you get the point though. The point is that the charge is inside that cylinder. In the middle, it's empty space here, charge, and then empty space, right? So in the middle, it's empty space. Then you have this charge, and once you go outside the cylinder, it's empty space. Okay, so how many regions do we have here? How many regions of space? Well, we got the inside, right, region 1. No. Okay, region 1. Then we got region 2, being the cylinder itself. And region 3 is outside the cylinder. Okay, so we got three regions of space here. Okay, so we're gonna find the electric field for every single region. So let's do region 1 first. Region 1. Okay, so region 1 is when I'm talking about when my Gaussian surface, lowercase r, is less than, oh, I just realized I did not define my different radii here. Let me do that in a different color. Okay, so we have capital R in. No, that should be out, the outer surface. So that's the outer surface there, R out, and then we have the inner surface, which I will call R in. Okay. And then again, all our charges is in here. Uniform charge, uniform distribution of charge. Okay, so so going back to my region 1, I'm looking at the region when R is less than R in. Okay, so that means when I pick my Gaussian surface, I'm going to pick my surface to be within that region. Now, what kind of surface should we pick? You know, what shape should we pick for our Gaussian surface? Well, we're talking about a cylinder here, so it'll probably be best to choose a cylinder. And let me draw an axis here, at least a faint axis. Okay, so here's this axis of the cylinder. Yeah, kind of supposed to look like it's going through it there, through the middle. And so I'm going to pick my region here, or my Gaussian surface. Look like this. Probably move that. Oh, come on. It's just faster if I just erase it. Ugh. So, gosh, so much work just to do that, but this is region 1. All right, so my Gaussian surface is a cylinder. Best as I could draw a cylinder, I think. Okay, so there's my cylinder on the axis of the coaxial with my my cylinder there, so it matches the symmetry. If you want to see it down here in this picture, I'm putting my radius like this. All right, and I'll call that radius. Oh yeah, that's way too big. That, of course, is my lowercase r. Right. I know it's getting a little small there in my picture. Okay, so okay, so we have lowercase r, and we are looking at when lowercase r is smaller than Rn. All right, so there's my Gaussian surface, right, which is like half the battle. If you pick your Gaussian surface into the right surface, all the rest of the calculations should fall in place. Okay, so we have flux equals charge inside your Gaussian surface over epsilon 0. Okay, and let's do under it. And flux is just EA. But what's Q inside? Q inside is how much charge you have in your Gaussian surface, right? So how much charge do I have inside my Gaussian surface? Or you could look at it here. How much charge do I have inside this Gaussian surface? If I'm in the middle of the cylinder, you know, all the charge is in the cylinder itself. It's not in the middle, right? All this is empty space. So I have 0 charge in here, no charge inside there. So this is going to be equal to 0. Okay, now flux can equal 0 in 2 ways. Either it equals 0 because you have as much flux going in as you do going out, or it's 0 because the electric field is actually equal to 0. In this case, it would be the latter. Electric field would be 0 because you don't have any electric field going, some electric field going in, some electric field going out. You would have to have either something weird like some positive charges in there or negative charges, you know, something where the electric field is going in and out. A good example of that is what I showed earlier. When you have a Gaussian surface here, and you have like a positive charge here. Okay, in that case, your flux is going to be 0, not because electric field is 0, just because you have some electric field going through here like this, which is a negative flux. Then you have positive flux. Okay, so it would be incorrect to say electric field is 0 there, because there is electric field. But okay, so I can't erase that. But in this case, you don't have that issue because there's of that symmetry, right? You have these charges symmetrically around here, and so from a symmetry perspective, all the electric field on the surface, right, on the circle, is going to cancel out because of that symmetry. So in this case, a 0 flux means that E equals 0. Okay, so my electric field in region 1 is 0. No electric field in region 1. Now let's look at region 2. Okay, so region 2, go here. I'm going to have to redraw my Gaussian surface. So when I talk about region 2, I'm talking about when Rn is less than R, but R is less than R out. All right, so I would redraw my Gaussian surface. I have to be really careful how I do this. No, it's not going to look great. So my Gaussian surface looks something like that. Let's do that. Okay, so there's my Gaussian surface. In the other picture, my Gaussian surface is, it's going to be kind of hard to tell because it's dark. Ugh, should pick a different color. Something like that. Okay, so it's in there. So I do have charge inside this, and that's going to be the trick here. How do you find that charge inside the Gaussian surface? So region two is going to be the trickiest part here. Okay, so let's do this then. So I have flux. Flux equals Qn over epsilon 0. We have the symmetry matched, right? So we have a cylinder for our cylindrical charge. So the flux just becomes EA. Charge inside. So it has a uniform charge distribution. We're just going to say, and I probably should have said this in the text here, uniform charge distribution rho or something like that. Charge density. Okay. So I'm going to use my my rho is a charge density of my cylinder. So I'm going to use that to find Qn. Okay, so we're going to go back to this equation. And put it off to the side here. Q inside equals charge density times volume. Now, which volume are we interested? Well, we're interested in the charge within my Gaussian surface. Okay, so it's getting that VG that's kind of hard because it's not just VG here. Where is my charge inside? My charge inside is right here, right? It does not include this big empty space, right? Because there's no charge in here. The only space I have charge is within this radius from Rn to capital or to lowercase r. For us to change the size of that. Let me see. I don't know if I could erase all that coloring. There we go. Okay, so I'm within my cylinder, and I want the charge just inside my Gaussian surface. So how do I find that? Well, let's just talk about, this is just a kind of a typical geometry problem. Well, not typical, but it's a little bit harder. So if I want to find this volume here, not the volume of the whole cylinder, but just this volume here, I need to find the volume of the whole cylinder itself. So the whole cylinder, let's say it has length L. The volume of the cylinder is pi r squared L. Okay, so that's this whole volume here. Everything inside my green circle, or everything inside my green cylinder. Okay, but is there charge everywhere inside my green cylinder? Well, the answer to that is no. You don't have charge everywhere in the cylinder. There's empty space right here. Okay, so this is empty space. So in my calculation for volume, I don't want to include this empty space. So I need to subtract out the empty space by that volume. So how much volume is empty? Well, pi Rn squared L. Okay, so this is the volume of where my charge exists. Okay, I hope that makes sense. It's not the volume of my Gaussian surface, because like I said, there's not charge everywhere inside my Gaussian surface, right? The charge density here is 0. So I wouldn't want to apply my charge density to this empty space. I'm just interested in this space right here. This a little sliver of the cylinder. Okay, so here's my volume that I'm using for my charge inside. So I'll do let me move this, give myself a little bit more space, and Qn becomes charge density times that volume, pi r squared L minus pi Rn squared L. I know a little harder there. Definitely a little harder because you have that volume, right? You got to subtract out the empty space where charge does not exist. We can't, if I didn't subtract out this space, then it will be as if this whole thing was filled with charge. And of course, that's not our problem. All right, so we're almost there. We need to solve for E, which means I need A. So what's the surface area? So I have electric field. This is a infinitely large rod. I have electric field like this. I don't, let me be careful my angles there. Okay, I don't have electric field coming out like that. Okay, that doesn't exist. This is a very long cylinder of charge. I'm taking it to be like an infinitely long wire. Okay, so I don't have any electric field going that way. So let me get rid of those. So I only have flux going through the edges, the sides here. I don't have flux going on the right face. I don't have any flux going through the left face. It's all through the edges. So I need the area of this edge, okay, of the sides here. If you imagine this was a can, like a soda can. I need the area of the sides of the soda can. All right, so how do I find the area? Go back to I think it was the first video of chapter 24. I explained how to find it. So I'm not gonna go into detail here, so you can always go back. But the electric field times the area is 2 pi RL. And I have equals density pi r squared L minus pi r n squared L over epsilon 0. Now, let me give myself a little bit more space here. My goodness, I can't select it. All right. I'll try one more time. Let me try one more time. Okay, I'll take it. All right, so now here is my equation, and now I want to solve. Okay, so let's solve for E. So it's just gonna be some simplifying. Let me see, what cancels out? Okay, so the L's cancel out, which is very typical when you deal with cylinders. These L's go away. The pi's cancel. And I think that's the best I could do. I mean, you have some canceling with the R, but then it just looks messy algebraically. So I'll just keep it like that and solve for E. So E, my expression for E equals, let's see here. Rho over 2 epsilon 0 R times everything in my numerator here. What's in my numerator? R squared minus Rn squared. Okay, so there you go. There's my electric field. At some distance R from the center. Okay, so this is electric field for region 2. Now when you get to region 3, which unfortunately I'm going to have to do in the next page, when I get to region 3 here, and I'll go back in a second. Now I'm looking at when my Gaussian surface is greater than R out. So R is greater than R out. So let me do some erasing here. Okay, so I'm going to take this circle. I don't know if I'm going to draw it in my other picture. Okay, so now my Gaussian surface, my Gaussian cylinder, right? It's outside the cylinder. Remember, the charge is just in here, just inside here. Okay, I would draw it in again, but it got messy last time I did that. Okay, so the charge is just inside my cylinder. So I want to find what is my, what's my electric field on this Gaussian surface? What's my electric field at this point, or at this point, or at this point? Right, the electric field is going to be the same no matter where you're looking, because of symmetry there. Okay, so let's start with Gauss's law. I have my Gaussian surface, so let's go back to Gauss's law. Flux equals charge inside over epsilon 0. Okay, charge inside here. Let me actually redraw it over here so I don't have to keep flipping back. Okay, so remember I have all this charge here, right? Oops. All this is my charge right inside there. Okay, so inside my cylinder I have charge. So when I ask the question, what's Q inside? Right, what's Q inside this Gaussian surface, my green circle? Well, that's just a charge inside here. Okay, so I need to find the charge. To find the charge inside, it's going to be charge density times the volume of the charge. Because now there's all this empty space, right? I don't want to include all this empty space. I don't want to include this empty space. And this volume, I just want to include where the charge exists inside my Gaussian surface. Okay, which would be right there. So how do I find the volume there? Well, remember our radius, we have R in and then R out. Okay, so how do you find the volume between R in and R out? Well, all we do is volume of a cylinder, so pi R out squared times L. Okay, that volume would be the whole thing, this whole thing here. But I don't want to include this empty space in the middle, right? There's no charge there, it's just empty space. So I need to subtract out this empty space. So it's minus pi R in squared L. Okay, so it's R in. Okay, and if you need to see it here, this is R in, and this one is R out. Okay, so that's my Qn. What about flux? What do I plug in for flux? Remember, flux is EA equals I'm like rho epsilon 0. Okay, what is the A? Remember, A is always the area of your Gaussian surface, in this case, a Gaussian cylinder. And we notate the Gaussian cylinder, the radius of the Gaussian cylinder, with R, right, lowercase r. Okay, so that means I'm going to have E and A, the area of my Gaussian cylinder. Well, it's the same area I had earlier, right? This area right here, 2 pi RL. It's just that now we're dealing with a different R. We're dealing with a radius that's larger than R out, but it's still the same area, the area of the sides of that can. So 2 pi RL, and then I have this rho. Factor out the pi. I'm going to factor out the L, and I'm left with R. Whoops. Over epsilon 0. Okay, so now let's solve here. Solve for E. So the pi's cancel. Let me see here. So this pi cancels with this pi. This L cancels with this L. And there's my equation. So my equation is E equals, let's see what I have here. Rho over 2 epsilon 0. R out squared minus R in squared over R. And that's my electric field. Okay, so let's put all these regions together in a graph so we can kind of see what's going on with the electric field. So I'm gonna do a little plot for my electric field here. Okay, so electric field on my y-axis, R on the x-axis, and I'm gonna have just a couple markers here. I'm gonna call this R in, my inner radius, and maybe a little more space here. R out, and I'll plot my graph. So what's R in? What's the electric field when R is less than R in, right, in this region here? Well, if you go back, what we calculated, we saw in region 1, which is R is less than R in, we saw electric field is 0. So I have a 0 electric field here. So let me plot that. Okay. So 0 electric field, no electric field at all inside. Now we get to region 2, which is this empty space, or no, the spot where there's charge, right, this charge here. So if I stay inside there and I start to, see what is my electric field within this region, well, this one is R squared minus R in squared over R. So what is that going to be? I don't know how that function is going to look like because R and R are variables there. So, So it looks like it's going to be linear, but it doesn't start at 0. Oh yeah, it does. Okay, so it'll be linear. I gotta convince myself of that. Let me just do it really quick. If I rewrite it just to see how it behaves, rho R over 2 epsilon 0 minus rho R in squared over 2. Oh no, it's not. No, that's not linear. Yeah, that's not a linear function. So it's, when Rn equals lowercase r, it's going to be 0, and then it's going to start to increase there. Yeah, I'm not exactly sure how it increases, how that function looks like, but it's not linear. Oops. Okay, so it increases in by some rate. Okay, yeah. So the reason why I did that is because I distributed this here just to see how the function looks like. So you have a linear function here, right, dependent on r, but this one's a 1 over r. This thing goes to 0 when lowercase r equals Rn, right? It'll go to 0. So it does start at 0, but once you start to increase your r, right, this term starts to increase, this term starts to decrease. So I think you would get like a curved function here. Anyway, not super important. So we see the electric field is going to be increasing, and then we get out here on region 3 when we're outside the cylinder. And when you're outside the cylinder, here's how electric field looks like: constant, except for this 1 over r. So it's a 1 over r drop. Okay. So that is how our electric field looks like. Put these little lines there. Okay, so this is the middle of the cylinder, right, the empty space. This would be in the cylinder itself. In the cylinder. And this would be outside the cylinder. Out of the cylinder. Okay. And maybe instead of middle, I should put center. That probably is more appropriate. All right, so that was definitely a tougher problem because you have those 3 regions in space. I think the trickiest part here And any of these Gauss's law problems that we're going to be doing, it's not so much A, right? A is just the area of the Gaussian surface. You do have to ask yourself, are we looking at the area of the ends here? Do we have electric field coming out this way, or is electric field coming out this way? Now for cylinders, electric field always goes out the sides. So the side of the can, if you will. So that's why we use the 2 pi RL. So area is not so much the tricky part. What's tricky is finding Q inside, because you have to ask yourself, what volume are you looking at? You know, in our case over here, you know, we're looking at the volume of the whole cylinder here, not the middle part, not the empty part inside, but the where the cylinder actually is. So you just got to be careful about the volume. Other than the volume, though, you kind of have a consistent pattern here, or a consistent approach. You start by drawing out a picture. You determine where your Gaussian surface is, right? All this depending on where, how large was my Gaussian cylinder, and then we go from there. We plug in for area, and we plug in for charge density. So we bring those two calculations that we've been focusing on, area and charge, together, and we solve for E. All right, so I'll do another example in my next video on what if you have a non-constant charge density. And then we'll be nearly done with chapter 24. Just one more video after that, but we're on our way. So we'll do more examples in the next video.